Welcome to the Lora Deep Dive, what the interviewer really wants to hear. In this session, we'll explore the art of moving beyond textbook answers to truly understanding two core questions that distinguish memorization from mastery in machine learning interviews. Whether you're preparing for your next big opportunity or refining your skills, this fine-tuning process will elevate your interview preparedness and set you apart in the competitive landscape of ML interview prep. Welcome to our discussion on the standard answer and why it's not enough. Often, people suggest freezing the original weights, adding a low-rank bypass, and updating only the A and B matrices during training. While correct, this response is overused. So let's delve deeper. Why does adding a small matrix to the original weights inject new capabilities? And how can a low-rank update matrix still be effective? Let's explore these core questions. In this section, we focus on Layer 1, which is all about accurate basics. First, we freeze the original debolted D-weight matrix, while only updating the smaller matrices B and A. This approach significantly reduces resource consumption. Next, we start by initializing B to 0, ensuring the model behaves as it did before training, with gradual learning of corrections. Finally, during inference, we simply merge without adding any computational overhead or latency. Welcome to the math at a glance. In full fine-tuning, every element of a model's parameters is updated directly. Lora, however, breaks this down by decomposing the update process. During inference, the first term represents the original model's output, while the second term is Lora's correction vector. This uses a rank constraint where R is much smaller than D, such as R equals 8 compared to D at 4096. Initially, B is set to zeros. In this critical layer, we explore what each weight matrix truly accomplishes. Imagine the matrix as a prism. Light enters as input and is refracted, guiding it towards the next layer. Lora introduces a correction vector, which nudges the output in new, task-specific directions without replacing the original weight matrix. Here, matrix A compresses input to isolate key features, while matrix B expands it back, ensuring every task is handled effectively. Welcome to our discussion on geometric intuition in rank R corrections. Here, we see that with R set to 8 and D at 4096, Lora modifies just 8 directions. These aren't fixed. The model learns which are crucial. Picture a river. A small upstream change leads to a vastly different course. This shift amplifies through layers, while 48 directions remain untouched, preserving the model's original capabilities and minimizing forgetting. Let's talk about why Lora resists catastrophic forgetting. A common misconception is that forgetting doesn't occur because the original matrix, W, remains untouched. However, during inference, we actually use W plus the change, delta W, so the matrix does change. The real reason is that the low-rank constraint channels changes into a tiny subspace, preserving most of the representation space. Plus, you can fully reverse the process by simply removing delta W, something full fine-tuning can't guarantee. Welcome to Layer 2, where we highlight a key insight. The low-rank constraint is actually a feature, not a compromise. You see, altering only 8 directions out of 4096 might seem like a limitation, but it's precisely this approach that makes Lora effective. By focusing on these few dimensions, we capitalize on the fact that fine-tuning is inherently low-dimensional, optimizing our model's performance without unnecessary complexity. Let's explore why the change in weights during fine-tuning, or delta W, can often be low-rank. Large models have billions of parameters, yet the crucial changes occur in a small, low-dimensional subspace. Pre-training already establishes general representations, so fine-tuning just tweaks a few specific directions. Think of it like annotating a world map rather than redrawing it. Research in 2020 confirmed that only a few dozen to a few hundred dimensions are typically involved in such updates. Today, let's explore the concept of intrinsic dimensionality in fine-tuning. Did you know that only about 1% of parameter updates are truly effective? The rest, roughly 99%, are just redundant noise. Research from 2020 found that fine-tuning on many NLP tasks requires adjusting fewer than 200 directions. Techniques like Lora, with a rank of 8 to 32, already capture the essential subspace. This means low-rank decomposition aligns perfectly with the real dynamics of fine-tuning. In this slide, we're exploring Layer 3's practical judgment for choosing the right rank when fine-tuning models. For simple tasks like sentiment classification, a rank of 4 to 8 is effective. More complex tasks, such as multi-domain instruction tuning, require a rank of 16 to 32. Beyond a rank of 64, improvements diminish. If R equals 64 isn't sufficient, full fine-tuning may be necessary. Be cautious of overfitting with excessive R values, especially with limited data. In applying Lora modules, the original paper showed strong results by adding them only to the Q and V projections in the attention layer. The Q projection guides what the model focuses on, while the V projection determines which information advances. However, in practice, incorporating Lora into all linear layers, including Q, K, V, output, and FFN projections, yields better results. Be mindful, though. This increases trainable parameters significantly, so consider your memory budget. Welcome to this slide on Lora versus full fine-tuning, and when to use each approach. Lora has a very low memory cost and a low risk of catastrophic forgetting due to its low rank constraint. It's fully reversible and works well with limited data, but it does have a moderate task complexity ceiling. Full fine-tuning, on the other hand, doesn't have a complexity ceiling, but requires more data and risks higher memory costs and catastrophic forgetting. Both methods have zero inference overhead. Welcome to the 4-step answer framework. First, in step 1, we freeze W, decompose it, and initialize B to 0, merging seamlessly during inference. Step 2 explains how addition works by using a correction vector to shift outputs efficiently while preserving the original space. Step 3 highlights the validity of a low-rank approach, emphasizing minimal adjustments within a vast, pre-trained model. Finally, Step 4 shares practical insights on rank selection and when full fine-tuning is essential. This slide is about what reaching Step 4 signals to an interviewer. It shows that you're not just someone who can memorize and recite mechanisms or equations. You truly understand Lora, explaining its geometric intuition and intrinsic dimensionality. More importantly, you've reached a level of mastery where you can make practical trade-off decisions, taking real engineering constraints into account. This demonstrates genuine engineering judgment in real-world projects. Let's review the key takeaways. First, addition acts like a directional correction, guiding Lora to make precise adjustments rather than random changes. Second, low-rank tuning aligns with the true nature of fine-tuning, offering genuine mathematical insights. Third, remember that rank is a design choice. It's about matching complexity, not just increasing size. Lastly, apply this approach across all linear layers for optimal performance within memory limits.